You got the memo? Yeah, we have our first lab meeting today, so I see some of my lab members not wearing their shirts. But they're probably not coming to lab meeting today. Are you? Yeah, I told Brittany about that. So I'm on it. It's not a requirement. It's just for fun. Okay. Is it time? Yeah, it's time. All right, you guys, happy Friday. It's still summer. We still have really nice weekend ahead. Okay, let's continue the very fun thing that you all love to do, calculations. You still have your papers that you were doing calculations on. So let's pull those out and finish the last set of calculations. And as a reminder, this is for a +5. I don't know if I said that already, but for Nigel, who's going to be collecting those, it's +5, not +2. Yeah, it has the ones that they're giving you today, all the calculations they've been doing. So this is for +5. And then the one due Monday, if you want to do it, the question number 7 from sampling chapter, that's also a +5. So nothing is mandatory when it's extra credit, but it's good for you. Chapter 5 in your book, the sampling, it was the lecture we finished 2 lectures ago, the last slide.
It was slide number 2 on the sampling prep.
Okay. All right. Okay. More pink shirts. All right. Let's get going. We were talking about buffers last time. And can you define pKa again for me? Do you remember? You want to give it a go? What is pKa, Mitchell?
When the acid.
Conjugate base.
Yes.
Yeah. Equal. Okay. It's the pH at which we have equal concentration of conjugate base and acid. So the log here of 1 is 0. Okay. And it's the maximum buffering capacity. I want you to remember this Henderson-Hasselbalch equation. It's not very hard to remember if you know the definitions, and you will need it for calculating buffers, how to prepare buffers. So this is something you need to learn, okay? You remember. All right. Let's work on this exercise. It will get you ready for next week's lab. One of the pre-lab quiz questions is buffer calculations, and in lab you will be preparing a buffer next week. Okay, so as always, read the questions and list your given. Okay, so read the question and list your given. Always, this is how you start. Why do I turn this over? It's making a noise. Okay. So let's list our given. I want a pH. I'm gonna start here so that I have the entire board. So I want the pH of 4.6. That's the buffer target. I want 1 liter of, what is the molarity? I need to prepare 1 liter of 1 molar buffer. It didn't say 1 liter, I'm just telling you, let's assume 1 liter. 1 molar buffer. So this is what I'm after. What am I given? They gave me the dissociation factor, Ka, of the acid. So they gave me the dissociation factor of the acid. That means the dissociation of the proton. And that was 1.74 times 10 to the negative 5. I need the pKa, which is negative log the dissociation factor. What else I was given? Oh, 1 liter, so the liter is there, okay. I was given the concentration of the stock solutions. So the stock solution that I have, oh, I shouldn't go up, right? Acid or the HA, okay? So the HA, or is it AH? How do I put it in the equation? I think AH is how it's. The protonated or the protonated form of your acid. Okay, the stock solution is 3 mole. Okay. And then I was given the conjugate base. Get that out of the way for a second. The conjugate base is your sodium acetate and given as a powder, a solid. So sodium molecular weight is, what is it, 80 grams? 82? 82 grams per mole. All right, this is all my given. What is the first step? What equation do I need? On the former slide, go ahead. Yeah. Yes, so the first thing you want to calculate is your pKa. Who can use the calculator to get me the pKa value? It's 4.7. So 4.7. 59. I'm just gonna say 4.76. All right, and then you said, Sophie, is the Henderson-Hasselbalch equation. So pH equals my pKa that I just calculated log of the concentration of my conjugate base over the concentration of my acid. Next, I can just put in the final pH that I want is 4.6 equal the 4.76, which is the pKa of my acid, plus log this ratio. Okay. So just bring that the 4.67 to the other side. So it's 4.6 minus 4.76 equal log A minus over B. All right, can you get me the value of the ratio now? Of A minus over AH. Just give me the ratio based on this using your calculator. So what I want you to tell me is what's the ratio of this? By solving this equation. So it's negative 16. What's the log of negative 16? Anti-log, I guess, right?
0.16.
Huh?
0.16.
0.69, you said?
Yeah.
Okay. Let me just double check that this is the right value. Yes, correct. Are we all following? If you're not following, please let me know where I lost you and I can repeat. It's okay for me to repeat. All right, so you're all following. Okay, very good. All right, so now I have this ratio. And do you remember last time when you want to prepare a buffer at a specific concentration, you assume it as a whole, a one whole part. And let's say if the one whole part is 1 molar, okay, then 1 molar equal the concentration of the conjugate base plus the concentration of the acid. It's a whole, 1 whole. You want to prepare a buffer that has both of them. So 1 whole, and in this case, it's 1 mole. Okay, so if I want to solve this, I want to unify solving for X. So if I want to solve for conjugate base, what would be AH? What would I replace AH by? Huh? 3, you said? Okay, so if I want to replace AH in an equation that has A minus so that I can solve for A minus, what would I do, Kristen? If you look at this equation here, forget about the concentration that you have. If you look here, so 1 minus equal this, right? So you can replace AH here and solve for A minus. So you can say, all right, here. A minus over 1 minus A minus equal 0.69. All right. What is A minus? Kristen, are you following? Does that make sense to you? Okay, very good. All right. solve for A minus B. If I want to do the algebra here, it would be 0.69 minus 0.69 minus, is that correct? Yes. And then if I bring that over, it would be 1.69 A minus equal 0.69. So equal 0.69 divided by, huh?
0.41.
What were you going to say? Greg?
Same thing.
All right, so give him his credit. All right, what was the number?
0.41.
0.41. All right, so now what is AH? Now that I have A minus, then I go, okay, so 1 minus, right? 0.41 equals my concentration of AH. So what would it be? 0.59, right? Right, 0.59. All right, so now I have what I want is I want 0.41 molar of A minus added to 0.59 molar of AH. I want to put these together and form that 1 liter, make that 1 liter of buffer. Are we all following so far? We're not done yet, but are you following the logic here? All right, please tell me if you're not, and it's okay if you're not. You're seeing this for the first time. All right, we're cool. Can I erase everything else on that side? Continue the calculation. All right, so we'll keep this here, and then I'm going to erase this part. Are you guys okay erasing this part? All right, so now I know the molarity that I want for my acid, and then the molarity that I want for my base or conjugate base. Now I look at my stock solution. I have the acetic acid, I have 3 molar. What do I want? I want 0.59 molar. What do I do? What equation I can use? Remember the equation of concentration times volume equal concentration times volume? Okay, so I have the 1 molar, the 3 molar stock solution. So how many milliliters of this I want to get the concentration of 0.59 molar? Can you see, or is this high? You can see? Yeah. All right. Times, what's the final volume I want? 1 liter. All right. So, all right. Now, calculate for me this.
Why did you use the 0.59 molar instead of the 0.41? How did you make that determination?
0.59 molar is my acid, right? So the AH is my acid. And my stock solution is of acetic acid.
Okay.
So I got the final concentration of the acid I want in my 1 liter of buffer is here.
Okay.
So, and now my stock solution is 3 molar. Does that make sense, Sophie?
Yes.
Okay, thank you for asking. All right, so what is my X in this case? Who has that? Tina.
196.67.
196.67, I'm gonna round it up to 197. just for ease. Let me confirm my value. Yes. All right. All right, so I need 197 milliliter of my stock acid solution to put in a volumetric flask that I'm going to have. It's a 1000 milliliter that I'm gonna mix my buffer components in. That's the acid. Now I need to know how much I need of the conjugate base. What's the given? I only have the molecular weight, so what do I need to calculate? The moles, I already have the moles, right? So I have this much in a liter, 0.41 moles per liter. So what do I need to calculate now? I have moles, I have molecular weight. The grams, I need the weight. It's a powder, right? It's a solid. I need to see how much I need to weigh out to give me 0.4 molar concentration in 1 liter. Okay, so I need to get to this concentration from a powder. All right, so number of moles equal 0.41 mole, right? Because in 1 liter, 0.41 mole per liter. Okay? So I have this much. This is my number of mole. Equals mass, which I need in grams, over the molecular weight. What's the molecular weight? 82. What's the unit? Grams per mole. Thank you. It's very, very good. You need to know your unit so that you know what cancels out. We're measuring grams. So mole here and mole here cancel. All right. So what is 82 times 0.41? Say that again loudly, please. Grams. 33.
33.62.
33.62 grams. Very good. Let me check my numbers here. 33.46 is what I have. Oh, I didn't round. Never mind. It's okay. It's just a matter of different rounding. It's fine. All right. It's okay. What's that?
Okay.
Well, I would like to laugh. What did Bram say?
I just said last.
Okay. All right. Okay, now what? So I have my 197 milliliter. What I will do is in a weighing boat, I will weigh this much. And then I bring it here, I'll put a little bit of DDW. But it's always better to dissolve. If you want the correct lab way of doing it, you will weigh it, put it in a beaker in, let's say, 400 milliliters of water. And then put a stir bar and just put this that you weighed in that beaker, let it stir, take that 400, put it here, add your 197. Okay, 197 milliliter of your acid. And then make up the volume. Anxiety is the worst. Make up to 1 liter with DDW, double distilled water or deionized distilled water. Okay, so you won't make this with anything. Okay. Is that clear? Okay. So here are the calculations. The reason I have different number is I didn't round. I put 0.408 instead of rounding it to 0.41 and 0.592 instead of 0.59. So that's the only difference here. These were rounded. Here I didn't round. So it's good to take a picture of this and also our systematic way of calculation. Okay. So there is this way of calculating for buffer, and there is another way that I think is simple or simpler, which is this way. You can take a picture of it. The way there's another way of doing it is unifying the molarity of the acid and base. And then just mix volumes. So meaning prepare 1 molar of acetic acid, prepare 1 molar of sodium acetate. So now we have 1 molar of each, right? And then the final volume would be 1,000 milliliters. So the ratio of the conjugate base to the acid would be, instead of putting a molarity here, we'll put the final volume. And then we will determine how many milliliter we need from conjugate base and how many milliliter we need from the acid. Then we mix them together, they equal to 1 liter. This way, it's just a different way of thinking about it, is unifying the units, prepare 1 molar of each, and then just mix volumes together. So whatever way you find easier for you, use. So that's why I provided 2 ways. Okay? Any questions? You can take picture. You know what? Can send one of you, anybody, send me an email. I can post this online with the solution. Why won't I do that? Having you take pictures. Duh. Can someone remind me? If I don't post it, one of you send me a note. So I'll post that with calculations. All right. Any questions? All right. This is what we're going to do next week in lab. So chapters in the introductory chapters in the lab manual is all about dilutions and buffers and preparing reagents. So it's a good read, bedtime story, to read them. And then the chapter that you're going to be working on next week is chapter 7. Now your notes online says a lab addendum. I did not update that. I apologize. We have a new lab manual, and this has been included as a chapter in your lab manual. So you don't need any addendums. It's a chapter 7 in the lab manual. Okay, and complete pre-lab quiz. You're gonna do calculations, and during the lab, before you start preparing your reagents, a TA will come to make sure that your calculations is correct. So if your calculations are not correct, it will mess up your reagent. So make sure a TA checks your calculation before you do the different sections of the lab. You don't need lab addendum, you need lab manual. Oh, geez. Okay. Yes. Yeah. So the pre-lab quiz has a bunch of calculations that you will need for the lab.
So not in our notebook, we'll do those.
And you need them in your notebook.
Okay.
So it's double, solve them in your notebook and then type them, or yeah. I just I corrected one place and I didn't correct the other. Yeah. All right. So moving on to my favorite topic or second favorite topic. You're gonna guess what is my first favorite topic. Protein characterization chapter is my favorite topic. This is my second favorite topic.
How many bonus points for that?
Well, you know, I appreciate you. How about that? So, chromatography. Who can define chromatography? I have stories to tell you. But before I tell my story, which my PAs have heard 100 times, what is chromatography to you? What does it mean? Does it ring the bell? One word. Hey,
Or I guess separation.
that's your word. Well done. Separation. Chromatography is separation. Based on what? Colors. You use columns, but you can use papers too.
Size.
Based on size. Well, okay, so size is one characteristic. So separation based on the characteristics, the properties of the compounds. Okay, now my story. So my daughter now, this is the first year I teach this class where my daughter is older than me. She's 22, or most of older than most of you, I should say.
She
Huh? So I've been telling this story since she was 5 years old, but no, this story actually when she was 10 or 11. Okay, who remembers a store in the mall called Justice?
Oh,
Tell me about it. What is
My
it?
mother spent so much money in that store. Everything was bright and patterned and glittery. And
Pink and purple.
sometimes the sequins would change colors with your hands. And great. That looked like that's like.
You know, Gen Z's, welcome. So, that was my nightmare. Let me tell you, that store. Okay. So I'm walking with my 10, 11 years old in the mall, and we get to that store. She goes in and interacts with every single item in the store. It's like taking her time, and I am ready to leave. I don't want to interact with anything. I'm just standing at the door. What happened? We separated. Right? We separated. She's in the store interacting with every possible item, and God get me out of the store right now. So that's me, that's her. We differ in age, we differ in likes and dislikes. So we got separated. Now, how do I get her out of this freaking store? She's just there. She won't get out. What do I do? What do I do to get her out? What would your mother do to get you out?
My mom always let me buy one thing. There you go.
Buy at least one. Well, your mom was strict. Sometimes it has to be more than one. But you would buy her something, and then now she's walking out of that store with something in her hand. She eluted. That's the proper word. Eluting out of the column is eluting. So she left because she had something. So there is a mobile phase and there's this stationary phase in chromatography. Stationary phase is that store and everything in it. And she's the molecule that is interacting with everything in the store. And if I want to get her out, is get her a molecule similar to what's there. So she would walk away with that mobile phase with the molecule so we can leave and go home. So that's chromatography in a nutshell for you. Separation base, you have to have separation. If you have no separation, there is no, if I take her with a friend,
No. No. If some of you know Emily, Nelson was, she's in food science, just graduated. She works in our lab. She was my daughter. She still is my daughter's best friend. If I take both of them to the store, they don't separate. So if I take them to Barnes and Noble, they will separate. One likes one type of books, the other likes another type of. So the idea is to separate your molecules, number one, then get them out. Otherwise, you're sleeping in the lab. You won't get them out. So you change the mobile phase characteristics so that you get your compounds out after they separate. All right, we can go home. That's it. That's chromatography. No, we still have. Oh.
Got me, yeah. Like, all right.
Are you? Come on, I'm telling you stories. You should be enjoying this class. Okay. At least I am. Okay, let's get down to business. The following intermolecular interactions are responsible for adsorption chromatography. I don't expect you to know what's adsorption chromatography, what partition chromatography, what size exclusion chromatography. We're going to learn all of that. But adsorption, from the name, the molecule is adsorbing to your stationary phase. What kind of interactions do you think is happening? Now, don't think about justice. There is no such interaction in that store. But what kind of interactions do you think happening? Sierra, sorry. A and B. All right. Any other answers or similar answers? B and C. Okay. Give it a go for a +2. Any answer gives you +2. Look at Ramsey. Yes.
I'm going G, all of the above on that one.
Wonderful. That is the correct answer. It can be any of the above. Now, there are specific adsorptive chromatography that we will learn about, like hydrophobic interaction chromatography. The interactions are only hydrophobic. But general term, adsorption chromatography, you have non-covalent interaction. You never want covalent interaction. It's very hard to break covalent. You want non-covalent interactions during separation. Only one type of chromatography, you don't have any molecular interactions. Can you guess? Somebody said something at the beginning. Go ahead, baby. Gas. Gas chromatography, there are interactions. You are going to say gas chromatography? In gas chromatography, your mobile phase is gas. So that's why it's called gas chromatography, but the molecules are interacting. Somebody said one word at the beginning. They separate based on size, right? So if you're doing size exclusion chromatography, your molecules are separating based on their size. So they're not interacting. It's an inner column, and it's like a gel filtration, basically. So they filter based on their size, molecular weight or size. Okay. Wonderful. Have you heard of reverse phase chromatography? Anybody? Nobody? What's up?
Are you disappointed in us for not knowing this?
Am I disappointed in you?
Yeah, for not knowing this.
Oh, no. I'm disappointed in my TA. No. No. I'm kidding. No. You have you heard of reverse phase chromatography? Okay, no, I know you're not supposed to answer. I just said to answer Razi, who am I disappointed in? Somebody.
I'm disappointed in myself, so.
No. That's why you're here, you guys. So, and we're gonna learn about something called reverse phase chromatography, normal phase chromatography, ion exchange chromatography. There's so many chromatographies that you're gonna learn about. And in this In reverse phase chromatography, your molecules are interacting with the column based on polarity via nonpolar interactions. And when they are interacting via nonpolar interactions and they separate the strength of these interactions, then your mobile phase, remember, you would have to bifurcate something, you would change the mobile phase to make them more nonpolar, and then your nonpolar compounds would be defined. So in reverse phase, if they are interacting via nonpolar interaction, which of the molecules will leave the column first? That's the leave first or move faster. Which one? Polar compounds will move faster because they don't want to interact with their column. And then the other thing is the mobile phase is polar because if your stationary phase is nonpolar, you want something opposite to enhance interaction of the molecule with your station. So A and C, and we'll, okay, if you don't get everything right now, we're gonna have more discussion about the different types of chromatography.
Huh. History. Who likes history? No. You don't want to learn about your ancestors in chromatography? Well, you know, so it started by this guy, David Day, who used earth, fuller earth, to separate petroleum. So that was the first application of separation using chromatography, but he didn't name it. He didn't give it a name. Then this guy came, Mikhail Svet, a Russian botanist, and he separated leaf pigments using chalk, a column filled with chalk. And he named the phenomena chromatography. Why? Why that name? Chromatography. Chroma.
Because
Color. The color. He separated color, leaf pigments. So chromogen. So he separated chromogen. So he called it chromatography. And he was credited. Poor David Day. He did chromatography before Svet, but Svet gave it a name and then he was credited by that. Partition chromatography and paper chromatography are the oldest forms of liquid chromatography. But gas chromatography in the 1960s became the most applicable, and they did a lot of advances, instrument and mechanics. And then the liquid chromatography benefited from these advances, like the column, the equipment used in the different parts. And then supercritical fluid chromatography also benefited from these advances. And we're going to talk about liquid chromatography a little bit about supercritical, and then Gary's going to come and talk about gas chromatography. All right, let's talk about some uses. What do we use chromatography for? In food analysis. Any ideas where this analytical technique is powerful? Great.
bond maps,
Huh?
bond maps,
What more?
bond maps, that's what I use them for.
What are these?
Remember, all exact right.
You do work with George? George. Okay, yes, we use it for oligosaccharide separation and characterization. Oligosaccharides, monosaccharides, disaccharides, larger carbohydrates like maltodextrin. Yeah, we use it for carbohydrate characterization. What else? Can you give another example? Amino acid, again from George's lab. So amino acid, so if you are trying to determine amino acid composition, you hydrolyze the protein into amino acids, then you put them on the column, And we'll talk about the method properly later on. And when they separate, you detect them, you determine the composition. What else? You've heard of. Huh? Organic acids. Okay, what else? Determining concentration of organic acid. And yes, impurities. Yes, any contaminants, adulterants like melamine, for example. Yes. What else? Flavor, absolutely. GC is for volatile compounds. Absolutely. What else? You know, you can go wrong. You can say anything. I'm going to say lipids, fatty acids, composition. Absolutely. What else?
I think if I saw these guys like maybe like a long one.
What's that?
I saw GC was like maybe like a long one.
Aromas, flavor. So basically, volatile compound. They call them volatile organic compounds. It can be, we call them sometimes flavors or odors or aromas or all this. You missed something very important. Protein. You just said what George likes to do. What about me? Okay, so proteins, flavors, carbohydrate, lipids, vitamins, organic acids, contaminants, phytochemicals, tocopherols, for example, different types of phytochemicals, antioxidant, hydroxycinamic acid, you name it, you can separate biochemical. All right, so uses, the sky is the limit, basically. And in food analysis, obviously, we use it a lot. Of course, they use it in pharmacology, they use it in different types of fields, organic chemistry, inorganic chemistry even. So it's used everywhere. So I have 4 more minutes. Extraction is the basis of chromatography. So basically, what is extraction? When you hear the word extraction, you're getting components out of a mixture, out of a complex system. So, and sometimes this component is soluble in liquid phases. And then they have separation. If you have 2 phases, let's say immiscible phases, hexane and water, your solutes might like one more than the other, and we call it having separation, coefficient of separation. So sometimes extraction is used as means of analysis, meaning the extraction that you do is the method for analysis. Who can give an example about a method of analysis that is based on extraction? I would say Tina knows, Caleb knows, Molly should know. I think you've been working with Coleman on that. What is it? What method of analysis is based on extraction? Mojana. Fat extraction method. So you extract the fat and then you measure the quantity and then you determine concentration. So that's method of analysis. Preliminary sample cleanup. So in carbohydrates, what do you do before you assess carbohydrates? If it's a complex sample, what do you want to do? Or even before protein extraction, what do? We remove the fat. Okay, so we defat so that the fat is not interfering in our next process. So sometimes we clean it up by removing some of the fat. And it's used to concentrate components of interest. For example, flavor compounds are present in very, very tiny concentration. So sometimes you extract them from other components to concentrate them so that you're able to analyze. So extraction is used in so many ways for analysis, for cleanup, for concentration. All right.
I'm not gonna start this video because it's gonna explain the process of chromatography and I don't want you to forget it over the weekend. So I'm going to wait till Monday. Have a great weekend, you guys. Yes, Nigel. We'll collect from you. I'm just telling them that. Give it to you.
Yeah, it is.
I have a question about,
Yeah.
about